Welcome back to The Explainer. Today, we're getting into something really crucial: how to master the performance of a semiconductor wafer fab. And I mean really master it. We're going to talk about moving past just gut feel and intuition and into a scientific approach that can, unlock a factory's real hidden potential.
All right, let's kick things off with a big question. It's a question that I'm sure keeps a lot of people in the semiconductor industry up at night. You've got these incredible, advanced wafer fabs. We're talking massive investments, the latest and greatest tech. So why do so many of them still underperform? Why do they fail to meet their true potential? Well, the answer isn't simple, and that's because a factory itself isn't simple. And this right here, this definition, is the whole key. A factory is a nonlinear, dynamic, stochastic system with feedback. Okay, that sounds like a mouthful, but let's break it down. It means things aren't straightforward. It's always changing. There's randomness you can't control, and everything you do has a ripple effect. And that complexity right there is exactly why trying to run a fab on gut feel and experience alone just doesn't work. In fact, it's almost guaranteed to lead you down the wrong path. All right, so here's our game plan for today. First, we're going to dig into that complexity challenge, why our intuition often lets us down. Then, we'll look at how to model the factory floor to really see the flow. After that, we'll do a deep dive into the anatomy of time. Seriously, where does it all go? We'll also cover the huge trade-off between capacity and speed, and then use a real example to find the true bottleneck. And finally, we'll bring it all home and talk about making that shift from gut feel to real science. Okay, first things first, the complexity challenge. Why is it that our gut instincts, which serve us so well in other parts of life, can just completely fail us on the factory floor? Well, it really boils down to two things: the incredible scale and the very unique structure of a semiconductor fab. Just picture it for a second. This is not your grandfather's assembly line, right? It's not a simple A to B to C process. We are talking about hundreds of individual workstations, maybe even thousands of process steps, all to make one wafer. The web of interactions, the dependencies, it's just staggering. It's way beyond what any one person can keep in their head. So the big question is, how on earth do you even begin to make sense of all that complexity? Well, it all starts with how you look at the factory, your perspective. We're going to check out two different ways to model the flow here, because trust me, how you see the problem, it completely changes how you solve it. Okay, so on the left, you've got the classic view, the workstation-centric model. This is basically a map of the building, right? Here are all the etchers. Over here are all the litho tools. It's how the machines are physically laid out. But look at the right. This is the process step model, and it shows us something way, way more powerful. It shows the actual journey of a wafer. It follows the product, not the machines, and that's a game changer. And this leads us to a word you hear all the time in fabs: re-entrancy. It's a really critical concept. All it means is that a job, a wafer lot, doesn't just go through the line once. It loops back. It might visit the lithography station, go do something else, and then come back to litho for a totally different step. It does this over and over. This reentrant flow is what makes a fab so incredibly different from a linear assembly line, and it just cranks up the complexity to a whole new level. Okay, let's shift gears to something that is absolutely critical. If you want to improve a factory's performance, you first have to know where the time is actually going. And I'll tell you right now, the answer is almost never what you think it is.
So let's do a little thought experiment together. Imagine you've got a fab with a 100-day cycle time. A wafer goes in, and 100 days later it comes out. Now my question to you is, out of those 100 days, how many of them do you think are spent with that wafer actually being processed? The value-added stuff, where a machine is physically working on it.
Yeah, the answer is pretty shocking for most people. Take a look at this breakdown. The actual time a wafer spends being processed, that value-added time, it's just a tiny, tiny sliver of the total. The vast, overwhelming majority of its time in the fab is spent doing, well, nothing. It's just waiting. Get this, in a lot of factories, it's more than 80%. Over 80% of the total cycle time is just waiting. Waiting for a tool to be free, waiting for a full batch to form, waiting for transport. This is what we call hidden waste. And this is crucial. It's not driven by how fast your machines are. It's driven by your factory's protocols and rules. So what's the big takeaway here? It's that attacking this huge chunk of wait time is your single biggest opportunity for improvement. It's the biggest lever you can pull. And in the world of semiconductors where the stakes are so high, just reducing your cycle time by 1 day, That can mean millions, and I mean literally millions of dollars straight to the bottom line.
And this brings us right to one of the most important, and frankly, one of the most misunderstood relationships in all of manufacturing. It's the connection between how much work you load into the factory and how fast that work actually gets done.
This chart just illustrates the brutal, unforgiving reality perfectly. This is what's known as a factory operating curve. Now look, as you move to the right, you're increasing the factory loading. You're using more and more of its capacity. Now watch what happens to cycle time on the vertical axis. It doesn't just go up in a nice, neat straight line, does it? No way. It curves up, and it curves up exponentially.
This is the danger zone. Once you start pushing your factory loading past, say, 85 or 90%, your cycle time goes absolutely ballistic. It just shoots for the moon. If you try to squeeze out every last drop of utilization, you will completely destroy your cycle time. Your factory becomes chaotic, unpredictable. The secret to running a stable, fast factory is to intentionally leave some capacity on the table. You need that buffer.
Okay, so enough with the theory, right? Theory's great, but let's make this real. Let's actually apply these concepts and see if we can find the real bottleneck in a sample factory. So, we start with the raw data, just like you would in the real world. We've got a simple little factory here, 3 workstations, 10 machines in total. And we have all the typical data: how much downtime they have, how often they're blocked, and their raw process rate, which is basically how fast they could run in a perfect world with no problems. But here's the thing. Raw process rate is a fantasy. It's a lab number. To find out what a machine can really do, its real capacity, you have to factor in all the real-world stuff. The downtime, the blockages, all of it. And when you do that math, you get something called the effective process rate, or EPR. And just look, a machine's true sustainable output is always way lower than what it says on the spec sheet. Okay, so now that we have this real-world accurate number, the EPR, we can do something really useful. We can calculate the occupancy for each workstation. That's just a fancy way of saying how busy it's going to be based on our production targets. And then it's simple. The workstation with the highest occupancy, that's your true bottleneck. And in this case, it's the machines that handle process steps 2 and 5. And this is the magic moment. Doing this kind of analysis lets you completely rethink the factory. You can take that spaghetti diagram of a reentrant flow in your head and transform it into this, a beautifully simple, straight line, decoupled flow. All of a sudden, you can actually see the real sequence of constraints. And once you can see them, you can start to manage them.
Okay, so let's pull this all together. What's the big lesson here? What's the main takeaway for anyone who's trying to manage a modern, complex wafer fab? It all comes back to this. A wafer fab is a nonlinear, dynamic, stochastic system. You have to treat it like one. You just can't rely on gut feel. You absolutely need a scientific framework. You need crystal clear definitions for things like capacity and cycle time, and you need models that are driven by real data to even begin to understand all those complex interactions. So I'll leave you with one final thought to take back with you. Look at your own factory's KPIs, your key performance indicators. Are you measuring what really matters for performance, like cycle time and variability? Or are you just measuring what's easy to see, like machine utilization? Because as we've seen today, chasing that last percentage point of utilization can be the absolute fastest way to kill your performance. The real opportunity, the big win, is in scientifically managing the flow.